Hello and welcome to this tutorial on solving constant coefficient and Euler equations. This is a concept covered in Math 2280 courses. My name is Sarah Wattups and I'll be walking you through just some simple ways to solve a specific form of differential equations. So first we're going to take a look at constant coefficient equations. We're only going to look at in this tutorial second order linear homogeneous equations. So just as a refresher, that means that it comes in the form ay double prime plus by prime plus cy equals 0. That singular y, not y squared, shows us that it's linear. It's second order because our highest derivative is the second derivative, and then it's homogeneous because it's equal to 0. So we're going to say that a, b, and c are constants, and we're going to assume that the solution is in the form we're going to assume solutions in the form of y equals e to the rx. So if we do that, we're going to want to substitute that solution into our original differential equation. And so we're going to take derivatives. The derivatives that's seen here, we just use a simple power rule there, and then we're going to plug those in, and we can then factor out e to the rx. So if we factor out e to the rx, we're left with this equation right here that looks like a nice quadratic equation, and this e to the rx is never going to be equal to 0 because it's an exponential equation. So we can basically ignore that, and we're left with this, which we're going to call the characteristic equation. So our solutions are going to come out of what our r is equal to from our characteristic equation. So we're going to solve for those roots, and we've got two ways to do this, basically factoring and the quadratic formula if factoring doesn't work. So three cases will come out of this. We've got distinct roots, repeated roots, and complex conjugate roots, and that just comes from going back to solving those quadratic equations. So case one, we've got those distinct roots, so we've solved and we got some kind of factoring that looks like we've got two separate factors, or we did the quadratic formula and we found two separate ones that are both real. And we get out of that two solutions, which is e to the r1x and e to the r2x, which gives us our general solution as a linear combination of these two, and as seen here. So our second case, is going to be repeated roots. And so if we did the same thing as the last one, our general solution is just going to be redundant. So we're going to add this extra factor of x onto y2, which gives us this as our general solution. So moving on to case 3, we've got complex conjugate roots. And in this case, it's going to give us y1 and y2, where we have cosine and sine paired with the complex part, or the imaginary part, the beta. And then we add on this e to the alpha x, which is our real part. So we put those together into a general solution, a linear combination of those two, and there we have our solution. And this is just an application of Euler's formula, which we're not going to get into today, but that's where those cosine and sines come from. So now we're going to move on to a slightly different type of equation. We're going to add extra powers of x to our equation. So it's going to look something like this: ax squared y double prime plus bxy prime plus cy equals 0. And when we're looking at a, b, and c, once again, are constants, and we're going to look at the same three cases, but this time we're going to assume that solution is in the form x to the r. So if we do that, we are going to take our derivatives, and then when we plug those derivatives in, it looks a little bit uglier, right? But we notice that each of those terms has an x squared with the x minus 2, or the x to the r minus 2. We've got the x to the first power with the x to the r minus 1. So those are going to cancel, and each of those terms is going to have an x to the r, which we can factor out. So when we do that, it looks like this, which simplifies quite a bit, and we're going to be left with another quadratic equation that we can solve. And we're going to assume in this case that x is not equal to 0. We're going to look at solutions outside of that. And we're going to call this equation the indicial equation. So looking quickly at those three cases, we've got distinct roots, where we're just going to put those roots into our original solution form and then into a linear combination of those. Then we have our case 2 with our repeated roots. Now in the last one we added a factor of x, but for Euler equations we're going to add a factor of ln of x. So that's the main difference. Other than that, our solutions are in our assumed solution form with our repeated root. So we put those together and we have our general solution. So case 3 is our complex conjugate roots, and this gets a little bit complicated, but it's once again separated into our real part with this x to the alpha and our imaginary part with our trig functions, and then we have an extra ln of x within those parentheses as well. So we put those together, and we have, these sine and cosines come from Euler's formula as well. But we put those together into a general solution, and there you have it. So I included some example problems with this video. For the sake of time, I'm not going to go over these in detail, but these show just 3 examples with numbers of constant coefficients. So you're welcome to pause the video and make sure that you understand these examples. And the same thing goes for these Euler equations. The same roots, just a slightly different equation form. And that's how we can get out solutions in a simple and efficient manner. But thank you so much for watching. These are my sources, and have a great rest of your day.